Hello everyone, welcome back to Arco Technophiles. Sorry, I have been in some other works and I am posting lately this video. So today we are here to learn about the difference between stiffness and strength regarding the steel. So let's get into the session. So the soul of steel. Why your flow don't bounce? This is because of modulus of elasticity E. So let's unpack the E. Actually its the value is 2 lakhs Newton per mm square. So what is the stiffness? For time being, forget the technical term for a moment. Stiffness is simply a material's resistance to deformation. Think of it as the material stubbornness actually. Stiffness versus strength. So the strength is Fy. How much force it takes to break or permanently damage the material. So the material will not get into the previous condition. So the stiffness is how much force it takes to make the material flex or stretch temporarily like a spring and again get back to the original position. So it is the experience of the material due to the stress only, but it doesn't physically appear in the material. The stiffness is the property of the material, but strength is the direct force applied on the material. Analogy: imagine a professional weightlifter. Strength is actually the maximum weight they can lift, right? But stiffness is how little their knee bends when they stand up straight. So the knee experiences so much of stiffness, so much of stress and all, right? So that is the stiffness actually. So for the caudal reference, actually this constant is enshrined in our national standard IS 800-2007, Indian Standard for Steel Design. Clause 2.2.4.1 states that the value of E for steel is taken as 2 lakhs Newton per mm square. Why this matters? This is not a guess, it is codified, reliable, constant we use in every calculation. For the reference, this is IS 800-2007 clause 2.2.4. So the physical properties of the structural steel, irrespective of its grade, may be taken as modulus of elasticity E equal to 2.1 into 10 power 5 Newton per mm square. So Newton per mm square can be written as megapascals also. Okay, we'll discuss in separate sessions regarding Poisson ratio, modulus of rigidity, coefficient of thermal expansion, and moment of inertia and all. Okay, so now let's go deep into the concepts, the stiffness versus strength. So why steel is so stiff? Actually the pure metal iron contains different atomic structure, right? It has same material. The atoms of iron combine like this. So if it is an alloy, the atomic structure of the that alloy will be different, so the bonding will be more actually. If you see, same one type of atoms only will occur in iron ore. So it will be layers will be regular and layer pattern will be regular. So the obviously the system will be soft. But when comes to the alloy, the mixture of metals makes the alloy strong, distorted layers. So layers cannot slide easily. So the friction will be more and bonding will be more. That's the reason the stiffness of the alloy will be strong and more compared to the pure metal. So the concept: stiffness is atomic strength. Steel, just as we discussed now, steel atoms are held together by extremely strong metallic bonds. You can visualize these bonds as tiny, incredibly powerful springs. When you pull or push the steel, you are trying to stretch or compress these springs, so which is very very difficult. So that 2 lakhs Newton per mm square is the measure of how much force those tiny springs exert to resist being stretched. So obviously the bonds, the atomic bonds will resist to get stretched or good to get pressed. So that is the stiffness. The deflection rises. Where does this number impact your life? Deflection. Engineers call it as sagging or bounciness, right? What is normally what do we call as a deflection? It is a sagging or bounciness, right? Scenario: a long steel beam spans across a room. When you walk on the floor, the beam naturally wants to bend, deflect under your weight, right? Here the role of E is higher the E, 2 into 10 power 5 Newton per mm square. The steel is extremely stubborn. It resists bending fiercely, and so the deflection is tiny. The floor feels solid. Here the stiffness of the steel is very high, 2 into 10 power 5 Newton per mm square. But when comes to the low E material, for example, if you take aluminium, it is having modulus of elasticity as 70,000 Newton per mm square. The material is less stubborn, it bends more easily, resulting in a bouncy or springy floor that makes you feel uneasy, right? So E and the stress strain curve. This is a very famous curve. For the engineers in the audience, here E lives on the most famous diagram in the civil engineering. On the y-axis stress is taken, on the x-axis strain is taken. If you see the linear curve, from origin to this position, it is in linear position, right? Then it got bent, and then again it is increased and come to the fracture level. I will explain each stage consecutively, okay? So understanding stress strain behavior. When you pull a steel rod gradually, elastic zone, so this is where it occurs. Straight line in position, stress is directly proportional to the strain, follows Hooke's law. That means stress is equal to E into strain. Modulus of elasticity multiplied by strain is equal to stress. The again strain will be change in length by original length, right? Material returns to its original shape when unloaded. So it is completely elastic zone from this to this place, okay? This is completely elastic zone. So that's why it is a linear shape. And next coming to the next stage, yield zone. Material starts to deform permanently. Stress remains nearly constant, but the strain increases rapidly. Stress at the stage is equal to Fy, yield strength. This is the most famous thing, Fy. In limit states also we will use. So we design the beams and columns and all, steel structures and all, to the yield strength actually. This is the, see, by increasing the stress, the strain started increasing, but it is not regaining. It is curvature, means it is having curvature, means it is not getting into the normal position. So it is non-elastic zone. So it is getting into the plastic zone. That's why that is called yielding. Yielding means the member will not get back to the original shape or original position. That's why it is in yield strength, okay? From this point the material loses its elastic property, so it will have permanent deflection. So coming next to the strain hardening zone. Stress rises again slightly as material becomes harder. So material becomes harder and stress again rises. So again after that the material becomes, after they are getting into the plastic position, that again the material will get hard. So again automatically the stress will be increased. So by after increasing the stress, it will reach a point called ultimate strength. So that is the maximum point of the material where maximum stress occurs. So after that ultimate strength, the material starts getting necking, and finally permanent fracture will occur. So this is what here explained. Necking and fracture. The specimen finally breaks. So maximum stress material can withstand. So the maximum stress is called ultimate strength, and without failure, but the material, see I will explain once again. In elastic zone the material will get back into the position. Okay, so shape and everything will be normal after removing the stress, but in continuation the material doesn't get back to the original position. That means strain is permanent strain. I mean no, the change in length or shape will be permanent. So that is called yield zone. So here the failure will not occur, but when it reaches when hardening zone, the stress will increase further, and finally it will reach ultimate strength. So after that necking and fracture will get started. Okay, the definition: modulus of elasticity is the slope of initial straight linear elastic part of the stress strain curve. Actually the modulus of elasticity is the slope of the initial or straight line. Okay, you have seen the, if you see the figure, you can see the slope, right? Modulus of elasticity is the slope of the slope of the straight line, linear elastic line, the part of the stress strain curve. So stress is directly proportional to the strain. That means it is linearly increasing. That means if you increase the stress, the strain will be increased parallelly. So E is the constant. Every time you apply stress, the strain stretching is perfectly proportional. E is the constant and of proportionality. That means steel stretching behavior is perfectly predictable right up to the yield point. Yes, this is what the main point we have to note. The predictable nature of steel can be up to yield point only. After that steel behavior cannot be predicted. Okay, so up to this point only steel position and steel behavior can be predicted. So the stress is directly proportional to the strain. So E is the constant. The slope of this line is called as modulus of elasticity. The steel is predictable up to this point. So why is this one number so important that we dedicated an entire session to it? Predictability. Because E is constant, we can precisely calculate the deflection. So the deflection can be precisely calculated, accurately calculated. The deflection of any beam or any column before it's built. No guesswork. So as we just say, because of the linear position, the predictability is very important here. The E is constant and we can precisely guess the deflection of the member. Next comes serviceability. Higher E ensures our structures are serviceable. That means serviceability criteria. What are the serviceability criteria? Deflections and cracks and all are called serviceabilities. So higher the E, if the material stiffness is more, that gives more serviceability, right? More life, meaning they are comfortable to use. No excessive vibration, no cracking, no cracking of finishes due to sag. Okay, serviceability is not regarding to the strength. Strength is a different concept. Serviceability is with respect to the deflection and cracks. So the deflection cracks criteria we have seen. We will further discuss the formulas also. The deflection and cracks comes under serviceability. Next, what is the third one is uniformity. Unlike concrete, which has highly variable E, steel's constant E makes it a perfectly uniform, reliable engineering partner worldwide. Why many prefer majority of structures with steel? Because steel nature is predictable. Concrete is a mixture of different materials. Of course, steel is a mixture of alloys, but concrete behavior is unpredictable during heavy loads and vibrations and all. But steel, until the yield point, steel behavior is predictable. That's why it is very famous because of the uniformity. So the main things why so many engineers prefer steel than concrete is due to predictability, due to serviceability, and due to uniformity. The engineer's daily checklist, where E is used. So we'll get into the some practical applications where we use E. The stiffness factor, deflection checks, serviceability. If a floor will slag or vibrate too much, the formula delta deflection is directly proportional to PLQ by EI is our guide. We use E to ensure occupants' comfort. So deflection is directly proportional to the PLQ by EI. P is the load, L is the span length, and E is the stiffness, modulus of elasticity, and I is the moment of inertia. So the combinedly EI is the exact combined stiffness of the material. That's why EI is combined. So next in application is load distribution in frames. In complex structures, stiff members attract more internal force. We compare EI values of columns and beams to ensure predictable load sharing. And third one is very famous thing, buckling and stability. The critical load of a column can carry before buckling depends directly on EI. So Euler's buckling load P critical is directly proportional to EI by KL square. Higher the E means better buckling resistance, right? Higher the I means better buckling resistance. So vibration and dynamics. Another one is natural frequency is directly proportional to square root of K. Increasing the EI increases the stiffness, which raises the natural frequency, often reducing unwanted vibration. So every time we increase the depth of the beam, we are leveraging the I in EI to meet deflection limits dictated by codes. The magnitude mystery. Y is greater than Fy. We may have a doubt. The material is experiencing, the materials is capable of experience 2 lakhs Newton per mm square, but Fy is only around 250 Newton per mm square. Why? The unit Newton per mm square is stress, force by area, used because E is constant material property irrespective of size. The magnitude E is the theoretical stress required to stretch the steel's double its original length. I will explain later. This concept I will explain in detail. Okay, it is a theoretical stress only. You can note it because it does not occur physically on the member. It is the capacity or the theoretical stress of the material property. It is the experience to such level. The conclusion: since steel fails at a stress of 250 Newton per mm square, that means hundreds of times smaller than E. It means steel is far stiffer than strong. Strength in stiffness is different. It stops stretching elastically and begins to yield long before it ever reaches 1% of its ultimate stretch. So, modulus of elasticity, steel is 2 lakhs Newton per mm square constant, and you know that concrete is brittle and it is having EC, modulus of elasticity of concrete, as 5000 F square root of FCK. Here FCK is characteristic strength of the concrete. It changes with respect to the grade of the concrete, so it is lower compared to steel. So these are the codal references. IS 800 2007, class 2.2.4.1 we have seen. IS 46 2000, class 6.2.3.1 for concrete. It was design focus. Strength led design. It is steel is strength based design. Concrete is stiffness led design. Okay. Relation between stiffness and strength. They are independent but connected. A structure can be strong but flexible like rubber. Stiff but brittle like glass. Deflection control. Beams and slabs serviceability depends on stiffness EI. Deflection limits in IS codes like span by 250 ensure that members are not just strong but stiff enough to resist the deflection and all, cracking and all. Frame analysis. Softwares like StatPro and SAP use the K factor, stiffness factor, is equal to EI by L cube in matrix analysis of structures. Buckling and stability. For columns we have already seen this. The critical buckling load Euler's load is P critical is equal to pi E square EI by KL square. Higher the E means or I means higher resistance to buckling. The slender columns larger L buckle more easily. So in vibration and dynamics also, natural frequency Fn is related to stiffness as natural frequency is directly proportional to square root of K. Increasing AI increasing stiffness, which increases frequency, reducing unwanted vibrations, important in high-rise buildings also. In layman's words, okay, let us forget long deep discussions in technical. Okay, in layman's words I will explain. Think of stiffness as how difficult it is bend a roller. Okay, you take a roller, it is very difficult to bend it. Okay, and strength is how much force it can take before breaking. We can break it easily. We can break a roller easily, but it is difficult to bend it to its ultimate level. A steel roller is stiff and strong, but a rubber roller is flexible but weak. In buildings we need both stiffness for comfort but strength for safety. Okay, strength is for resistance against breaking, resistance against failure. Stiffness is for resistance against lack of serviceability. I mean serviceability problems. That means deflections, cracks and all. The stiffness formula. The formula shows how the material E, the shape I and length L combine to determine the member's rigidity K. The stiffness K is simply force by deflection. Okay, force by deflection. For example, stiffness is what is that? Stiffness is force by deflection. So K is EI by L cube. E here, E is material stiffness, 2 lakhs value, we have discussed that. I is second moment of area, the shape's efficiency. A higher the I, example deeper the beam, drastically increase the stiffness. L cube is length, the deflection killer. Doubling the span means reduces stiffness by 8 times. If we make a span by 2L, automatically the stiffness will be reduced by 8 times because L cube means 2 cube, double the length means 2L, 2L cube, 2 cube means 8 times. So if you just double the span, the stiffness will get reduced by 8 times. So it is very dangerous during increasing of spans during structural designs. We have to be very careful with respect to EI. So for that we have to increase parallelly the depth of the sections and material property and all. What is EI? E equal to 2 lakh MPa means 2 lakh Newton per mm square really means. For steel, E equal to 2 lakhs MPa, that is 2 lakhs Newton per mm square, 2 into 10 power 5 Newton per mm square. This number does not mean you apply 2 lakh Newtons per mm square in reality. Instead it means when you apply 1 MPa, that is 1 Newton per mm square of stress, the steel will strain by 1 by 2 lakhs. That means the strain will be 0.000005. So E tells you the ratio between stress and strain, not the actual stress you apply. So the change in length is almost negligible due to elastic nature of the linear zone of the graph. And in other words, I will say the core concept. Within the elastic zone, the member experiences stress of 2 lakhs Newton per mm square. That means 2 into 10 power 5 Newton per mm square. That means 2 into 10 power 5 megapascals. For having strain of 1. That means the change in length of the section will be equal to the original length. Due to the high atomic strength, the member experiences such a stress of 2 lakhs Newton per mm square. Sorry, here I have to mention Newton. 2 lakhs Newton per mm square, as if to make the length double of its original length. But in reality, this does not exist. Sorry, not is not printed here. This does not exist physically, as it is a material stiffness property to such a capacity by atomic strength of the alloy material. This is the concept you have to get clear. So elastic modulus is E equal to 2 lakhs MPa, 2 into 10 power 5 Newton per mm square. Ratio of stress to the strain. Yield strength for steel Fy equal to 250 MPa, 250 Newton per mm square. Stress at which permanent deformation begins. This 250 is permanent deformation, where the permanent deformation begins. This is the 250. Okay. Stress equal to E into strain, because we have in other way you can say E equal to stress by strain. So within the linear elastic zone, if you apply 250 MPa stress, strain is equal to 0.00125, that is 0.125%. This is roughly strain limit for mild steel before it starts yielding. For HYST and all, it will be more, because the alloy structure will be different. So it will more yield point will be more for the HYST steel, because the permanent deformation occurs at higher stress. What happens after Fy 250 MPa? This is for mild steel only. Okay, you please remember that at Fy equal to 250 MPa per Newton per mm square, the steel started to yield, right? We just now discussed. Until that, it will get back to the original position. But Fy is the strength of the material property up to the yield level. Further, the material gets permanent deflection, so it will deform permanently. Even if you don't increase the stress also much, say if you increase the stress by 260 MPa, the strain increases rapidly still, because it stretches more and more, because it is crossed the elastic zone, and also permanent deflection or permanent deformation started already at 250 MPa. So yes, in the elastic zone, it takes up to about 250 Newton per mm square stress to stay perfectly elastic and come back. Beyond that, beyond Fy, that is yield point of 250 Newton per mm square for the mild steel, keeps deforming permanently even if you don't apply much more stress. Understanding the flexural rigidity and Euler's-Bernoulli's principle. Flexural stiffness K is directly proportional to EI by L cube, right? So here the stiffness K is member's resistance to elastic deformation. It is measured as force by deflection. Stiffness is force by deflection, right? E is the material stiffness, modulus of elasticity 2 lakhs Newton per mm square. The material is constant, stubbornness, and higher the E, stiffer the member. I is the geometric stiffness, second moment of area, measures how efficiently the cross section resists bending, because it is with respect to the shape of the material. The more area distributed in the line of the bending, it will be more stiffer. So it is geometric stiffness. So for example, if you take a roller, if you try to bend it along the web, it is very difficult to bend it, right? On the width direction, if you bend it, it will break easily, it will bend easily, right? So the web version will be having more stiffness, because the center of gravity, around the center of gravity more area is distributed in the line of bending. But if you bend it in the perpendicular direction, I mean on the width side, if you bend on the thickness side, if you bend it, the lesser area is distributed around the center of gravity and it will break easily, right? L cube, can I explain on the right page? Just a minute. So here is a roller, right? This is web direction and this is thickness. So if you bend it in this way, like means if you want to stretch it like this, right? Keeping it like this, it will be very difficult, because the center of gravity in the direction of bending is having more area around the bending part. See, like this. But if you bend it like this, that means if you make it like section like this, that means I am making a perpendicular section of this same roller. This is on thickness side and this is like this. Now if you bend it like this again, that means it will be bend easily, right? In this way it will bend easily, because the center of gravity in the direction of bending around the area is smaller, area distribution is smaller. That means it will break easily and bend easily. This is where I comes into picture. This is what is I? Moment of inertia. That is second moment of area. We'll go deep into the I part in the next session and coming sessions. Okay. So coming back to the presentation, L cube is the length. So deflection scalar, you have discussed it. We increase the length by 2 times. The stiffness will be killed by 8 times. Bernoulli's assumption by plane sections remain plane. What is Bernoulli's assumption? Assumes that strain across the beam's depth is linear. This simplifies the complex mathematics of bending. The material link. Stress is equal to modulus of elasticity into strain. Links the material stiffness to the stress and strain. This is Hooke's law. Okay. So here the governing equation is EI d square by dx square is equal to mx. Mx means bending moment. The fundamental equation states that the internal resistance EI into curvature, d square y by dx means curvature. So if y is the length, dy by dx is the linear deformation, and d square by dx square is a curvature deformation. Okay, so for the curvature it comes as d square by dx square. Must balance to the external bending moment. So this is the internal material property. So EI is the stiffness multiplied by the permanent deformation curvature should balance the external bending moment mx. Then only the structure will be in equilibrium and safe. The deflection formula, solving the governing equation, gives deflection is directly proportional to PLQ by EI. Stiffness, inverting this, K equal to P by delta. Right? We got it. So this is how formula is derived. Gives the final stiffness rule, E equal to, example, K equal to 48 by EI by LQ for simply supported beam with central load. Okay, we'll discuss all these things in coming sections. So a geometric nonlinearity, the axial load P acts on a member that has already swayed delta, create an amplifying secondary moment P delta, right? That is P delta effect. The secondary moment causes more sway, effectively reducing the structure's effective stiffness. So the IS 800-2007 class 4.4 requires engineers to consider the second order effects when the structure stiffness is low because of the slenderness. Euler's buckling stability. Critical load P, column stability is directly governed by EI. So we already know that P critical load is equal to pi square EI by KL square. K factor, effective length factor K, adjusts L based on end restraints, fixed pinned and stiffness stepper connections led to a smaller K value, drastically increasing the P critical. That means the critical load taken by the column. The simple stiffness formula comes directly from a classical beam theory built on these steps. Bernoulli's assumption, it assumes that plane cross sections remain plane. We have already discussed it. So here the mx is the bending moment, the mathematical representation of bending moment acting on the beam at any specific zone at any specific point x along its length. So for a distance at a distance of x, the bending moment is mx. Must be balanced by the E square dy by dx square within the material property, the stiffness of the material. So bending moment is a measure of internal forces that cause a beam to bend or rotate when load is applied. It is algebraic sum of the external forces, loads, reactions multiplied by the perpendicular distance from the point x where you are calculating the moment. Unit is equal to force into distance, typically Newton into meters, Newton meter or Newton millimeter. Why it is mx? The moment usually changes from one point to another along the beam span, so it is expressed as a function of the position x. Example, for a simply supported central load point P, the moment is 0 at the ends and maximum at the center. Okay. So E is the material property we have been focusing on in this session. The core concepts are all discussed. So here we can note that resistance to elastic stretch. Okay. After that, yield point occurs. Fy, that means 250, 415 or 550 like that, 500 like that, Newton per mm square. I, the second moment of area, diagram based on the diagram I explained, we already discussed it. So why it matters? I is a measure of how efficiently a cross section resists bending. The second moment of area, the moment of inertia, it depends on entirely on the shape and dimensions of the beam cross section. We already discussed it. And I beam and rectangular circle, length to the power of 4 is unit is mm to the power of 4 because it is second moment of area. We will discuss it. Why it matters? A deeper the beam has much larger eye, the shallow one, which is why I beams are deep, okay, than the shallow one. We discussed it. How beautifully the area is distributed when it is considering the web direction of the roller. So that's why it is taken more bending resistance, more stiffness it has given, geometrical stiffness it has given to the beam compared to the thickness in the width direction along the line of bending. So EA is the flexural rigidity. What is EA is called as the product of E and I is so important, it has its own name. What is flexural rigidity? EI. It is a measure of beam's overall resistance to bending, combining the material resistance and the shape's geometric resistance, geometric efficiency I. Units are Newton per mm square into mm power 4, that is Newton into mm square. This term is mathematical representation of beam shape. Generally in calculus, the term d square y by dx square represents the curvature of the deflected beam. Y is the vertical deflection sag of the beam at a position x. Dy by dx will give the slope of the deflected beam, the rotation. Slope means rotation. Vertical deflection means sag. Then d square y by dx square, the rate of change of slope, this is the curvature, and length is equal to typically mm. The complete equation E square by dy square is equal to E mx. This equation is the core of the Euler-Bernoulli beam theory. This states that at any point x along the beam, flexural rigidity is equal to curvature, that is equal to bending moment.